So we have something like solve x squared plus 4x plus 5 equals 0. And when I look at this, I notice that there's two terms that contain the variable. There's no way to make them into one term that contains a variable. And so because of those two terms, I can't isolate x. Or x squared, in fact. Right? I can't get either of those alone on one side with a constant on the other. And so that tells me that I have to factor. And so we solve this problem by factoring. Oh, I'm sorry. I switched those two numbers. It wouldn't have been factorable if I had. There we go. So x plus 4 times x plus 1 equals 0 gives me x equals -4 and -1. So that's what we did first. And then yesterday we noticed that if you have something like x squared minus like 7 equals 0, well, it's a difference, but it's not a difference of squares, right? Because x squared and 7 aren't both perfect squares. In particular, 7 is not a perfect square. So we can't factor. I don't know why all of a sudden I'm writing in red. But we can isolate x squared, right? We can get x squared alone on one side with a constant on the other side. So we can solve using that square root property that we talked about yesterday. So I can say x squared is equal to 7. So the square root of x squared is equal to both the positive and negative square root of 7. So x equals plus or minus the square root of 7. So this covers a couple of cases, right? This covers what to do if you can't isolate x, but you can factor. And it covers what to do if you can't factor, but you can isolate x, right? So those two methods take care of both those situations, but we don't yet have a method for when you can't do either of those. So for instance, what did I say here? 2x squared minus 5x plus 1 equals 0. So I have two terms that contain my variable, right? Which means I can't isolate either the x squared or the x, right? I can't get a term containing x on one side and a term or a constant on the other, or a term containing x squared and a constant on the other. Having those two terms gets in the way. So I can't isolate x or x squared. So according to what we did over here, that means I should factor, right? So the AC, let's see, AC is 2, B is -5, and then I run into some trouble here because there's no two numbers that multiply to 2 and add to -5, right? If they multiply to 2, my only options here are like -1 and -2. They add to -3, can't get up to -5. So I can't do either of those things, right? So I can't use the square root property because I can't isolate something squared, and I can't factor because it's prime. So we need another method. So there's two other ways that you can solve quadratic equations. One of them is called completing the square, where you use a specific method to rewrite this equation in the form that we talked about yesterday, like something like this, right? Where you can then isolate this guy and use the square root property. We're not touching that. If you take pre-calculus next semester, you will learn it, but if you take survey of calc, you'll never need it. So we don't cover completing the square, but we cover a really important result of completing the square. So somebody was like, oh, well, what if I look at for a general equation, so ax squared plus bx plus c equals 0, and did that process of completing the square, where you put it in that form where you can isolate x plus something squared equals a constant, and you take the square root of each side, and somebody did that with A, B, and C instead of specific numbers. And the result they got is a formula that we can use to find solutions to any quadratic equation. So the solutions are given. So what we're looking for is x. So we get x equals, and then there's this formula that's based only on the coefficients. So the opposite of b plus or minus the square root of b squared minus 4ac. I went a little overboard with that, over 2a. And this is what we call the quadratic formula. I'm not a huge fan of memorization, but you are expected to memorize this. That comes from over my head. So there's a song. There's actually several songs. The classic one is the Pop Goes the Weasel one. Like, it goes to the tune of Pop Goes the Weasel. Please don't sing it because it gets in my head for like 5 days. You can sing it in your own head, but if you say it out loud, I will never, ever stop hearing it. There's also like more modern ones. Like, I think there's an Adele, like, it's like a hello thing. There's so many of them. If you want to like go on YouTube and find a song that you're going to get stuck in your head so you remember the quadratic formula, more power to you. What I always do when I have to memorize something is I write it every time I use it. So like if you have a problem where you're going to use the quadratic formula, before you start plugging in numbers, just like copy it like this, and you write it enough times and then it becomes like almost automatic, like your hand will just do it for you. So that's how I remember things. Or, you know, you can make flashcards or put it on your bathroom mirror, whatever, so that you can read it a few times or write it a few times and memorize it. The quadratic, I will warn you, like, people really like the quadratic formula, and I'm not really sure why everybody likes the quadratic formula so much, because it's sort of one of the more useless things that you will learn in math. The reason being is that it only does one thing. So the only thing it does is give us solutions to a very, very specific equation, right? Only equations that are degree 2 polynomial equations can be solved with the quadratic formula. So note that it's not about how many terms there are. So if you have like x to the third plus 6x minus 5 equals 0, that cannot be solved using the quadratic formula because it's not a quadratic equation. It doesn't have degree 2, right? It has an x to the third in it. So like this formula is really, really specific as far as what it can actually do, and it's useful for doing that one thing. But like factoring, for instance, we have all these applications of, right? We've used it to work with fractions, we've used it to find LCMs, we've used it to solve equations, and there's a whole bunch of other uses that you'll use it for moving forward. The quadratic formula is sort of like one and done. Like you can do one thing with it and you can't really apply it to anything else. So it's useful in a lot of cases, but I warn you against like trying to like throw it at every single problem that you see, because like knowing that really well isn't really going to get you anywhere else. You know, whereas like knowing how to factor like actually is going to help you in every single math class you ever take. So we'll do a couple of examples with it. But where we're going to use this for the most part is in application problems. So specifically when you have equations that have like coefficients that are decimals and things like that, it's really impractical to try to factor those. And so this is really useful for that. So anytime you can't factor a polynomial, you should ask yourself if you can use the quadratic formula, but be careful about if it's actually a quadratic equation or not. So it only works for quadratic equations. Which these are degree 2 polynomial equations. So meaning that if there's x to the fourth, x to the third, x to the seventh, that's not quadratic, not going to work. So let's do a couple of examples, just kind of simple ones, and then we'll see like some other ways this can be used. So let's solve that one I just gave you. Solve 2x squared minus 5x, minus 5x plus 1 equals 0. So first thing I make sure of is that I have a 0 on one side and that this is indeed a degree 2 polynomial, so the highest exponent is 2. So that's all true, which means I can use the quadratic formula. Personally, I would try to factor first, but I see that AC, we already saw that AC is 2, that B is negative 5, and this can't be factored. So I'm going to say A equals 2, B equals negative 5, and C equals 1. So then I have X equals, make sure you keep that X equals there, just like we talked about yesterday. Over the next week, we'll see that we're doing a whole bunch of different things with the same functions and the same equations. And so it's really easy to get mixed up about exactly what you're finding if you don't consider the left side as well as the right side. So don't just plug things into that big formula and then have it hang in there. Make sure you say X equals so that you know that you found solutions to an equation. So we want the opposite of B. I hesitate to call it negative B because that sort of lulls us into thinking that it's always a negative number. Notice in this case that the opposite of B is actually positive 5, right? Because B is a negative 5. So this is going to be 5 plus or minus the square root of negative 5 squared minus 4 times 2 times 1. All over 2 times 1. So X equals, so the first thing I want you to do, and believe it or not, like the mistakes people make with these things are usually like calculator related, like plugging things in. What's up?
Oh, isn't it supposed to be 2 times 2?
Oh, yes, thank you. Thank you, I'm sorry. There you go, yes. So what I want you to do is in your calculator, just plug this entire thing in all at once. Not the square root, just what's under it. So that negative 5 squared minus 4 times 2 times 1. So 5, whoa.
It's the same both ways if you put it in the square root.
Right.
Yes,
Some calculators are gonna like give you a decimal for the square root. Like some calculators, like the calculator you have, will give it to you in terms of the square root. Like it'll give you like square root of what is this, like 17? Right. So we don't want the decimal. So that's why I say don't put the square root there, because if you have a calculator that doesn't do like the pretty print, like in math mode, then you'll just get a big ugly decimal, which we can't work with. So square root of, I believe it's 17, right? Over 4. And we're done. Like, that's all there is to it. We have not talked about simplifying radicals, so even if the radical can be simplified, we're not going to do it yet. So these cannot be simplified at all. The only thing you're doing here is figuring out what that number is under the radical, putting it under the radical, done. There's no way to simplify these. In particular, if this was like a 10, like you cannot do any of that stuff because that's addition and or subtraction in between those two terms. So you can't cancel a term. And we can't factor this because 5 and the square root of 17 don't have any common factors. So there's no way to get a common factor in the numerator and denominator. If you are getting negative 33, it's because you did not put parentheses around your negative 5 when you squared it. That's a really common error. If you find yourself making that error, you can drop the negative altogether because 5 squared is the same as negative 5 squared. So like you can type 5 squared minus 4 times 2 times 1 into your calculator and get the right answer every time and not risk making a mistake with the negatives. Did everybody get 17? Anybody not get 17? Okay. Like I said, the most common mistake with these is just punching things in incorrectly. So that's why we're kind of practicing that a bit. Okay, so let's look at another one. Let's find the x-intercepts of f of x equals 2x to the third, where is it, minus 6x squared minus 6x, 6x, there we go. So what's the first thing I have to do if I want to find x-intercepts?
Set equal to 0.
Yeah, you have to set your function equal to 0, right? You're looking for the solutions to f of x equals 0. So 2x to the third minus 6x squared minus, is that a minus? Yes, 6x equals 0. And then can I use the quadratic formula here? I cannot, and the reason is that this isn't degree 2, right? It's got an exponent of 3 in there. And so really the only chance we have at this point of solving this is if we could do some sort of factoring. And when I look at this, I do notice that I can factor out a GCF of 2x. So that gives me some hope that maybe I'm going to be able to solve this by factoring. So I'm going to go ahead and factor. So 2x times x squared minus 3x minus 3 equals 0. And then from there, I would be like, okay, now I want to factor x squared minus 3x minus 3. So I have an AC of negative 3, a B of negative 3. Does that factor? So I'll write it down. It's not really going to work, right? To get an AC of negative 3, like my only possibilities are like 2 and negative, or 3 and negative 1, or negative 1 and 3. And neither of those adds to negative 3. So I can't factor that, so I'm ready to break up my factors. So I have two factors, or the product of two factors equal to 0, so that means that either 2x is equal to 0, or x squared minus 3x minus 3 equals 0. So on the left, dividing by 2 gives me x equals 0, so that's one of my solutions. And then on the right here, well, it was disappointing that I couldn't factor, but what I did get from factoring out that GCF is that one of the equations, when I split them out, one of the equations is a quadratic, right? So now that x squared minus 3x minus 3 equals 0 is degree 2, and so that piece of it I can use the quadratic formula for. So this is quadratic. So I'm going to use the quadratic formula. So A equals 1, B equals negative 3, and C equals negative 3. So we have x equals, so the opposite of B is going to be a positive 3 here, plus or minus the square root of negative 3 squared minus 4 times 1 times negative 3. Over 2 times 1. So we get x equals 3 plus or minus the square root of, go ahead and plug that into your calculator. I got 31.
No, I think it's 21. Yeah.
Oh yeah, you're right. I'm sorry, 21, yes. Adding an extra 10. There we go. Everybody get 21 on their calculators? Again, just be sure you're plugging that in right with your signs and all that good stuff. And like, I would just plug it in all at once so you're not like making mistakes putting it together, trying to do it piece by piece. It's also quicker. So this gives us 3 solutions, right? So these are my zeros. 0, 3 plus the square root of 21 over 2, and 3 minus the square root of 21 over 2. There's one more step to do here, which is to write ordered pairs for my x-intercepts, right? So I found the zeros of the function. From there, I have to put them into ordered pairs with a y-coordinate of 0. So I get 0, 0, and 3 plus the square root of 21 over 2, 0, and 3 minus the square root of 21 over 2, 0. And so be really careful with these. Like, I will warn you, if you use the coefficients of this original equation in the quadratic formula, you will get those same 2 zeros because the coefficients didn't change when we factored out an x, right? I mean, we factored out a 2 also, but that cancels off in the end. But you wouldn't get that 0, 0. So the only reason that you get the same thing, even if you plug the original coefficients in, is because we were able to factor out an x and then get a quadratic, right? Like, that doesn't mean that any cubic, so any degree 3 equation, you can just plug the numbers into the quadratic formula and get the solutions. And if you do that, you'll always lose one of them at least. So be careful that you're actually separating it into the GCF equals 0 and a quadratic equals 0 before you start plugging things into the quadratic formula. So always check for that degree before you use the quadratic formula. So far, so good? Okay, so let's, what else do I want to say about that? Let's do this one. You guys try solving f or 5x squared minus 3x minus 9 equals 0. So give that guy a shot real quick. If you're using the quadratic formula, make sure that you start with x equals. So we get that, and then what'd you guys get under your radical? It's kind of nasty, this one. It's a big number. $189? Over 10. Is that what we all got? Still typing. Okay. Guys back there, did you guys get 189? Yep. Good. Okay. I tell you what, you guys are like the best listeners ever. Like, I've never had a class that, like, when I say, like, remember to write x equals or remember your parentheses, like, every single one of you does it every single time. I'm so proud. It's why you guys have the highest test grades in all the sections. I mean, it's awesome. Like, when I walk around the room and, like, everybody writes x equals, that has never happened before in any of my classes. You're my favorite. So let's talk about some other things that we can get from the quadratic formula. So it gives us these solutions, but it also characterizes solutions for us if we break it down a little bit. So if you have, we know that the solutions, so the zeros of f of x equals ax squared plus bx plus c are given by the quadratic formula, which is x equals, I like that line to be straight, there we go, negative b plus or minus the square root of b squared minus 4ac all over 2a. But in particular, part of this, why is this thing not working? Come on, buddy. There we go. In particular, the part that's under the radical actually classifies the solutions for us as far as like how many x-intercepts you're actually going to end up with when you graph this function. So this part of this formula, we call it the discriminant. equals b squared minus 4ac. And that part of it can be used to do some interesting stuff with our function. So the first thing we're going to look at is if the discriminant is positive, so if b squared minus 4ac is greater than 0, remember, no square root, right? The square root is not part of the discriminant. It's just what's under it. So let's think about this. If I have x equals negative b plus or minus the square root of some positive number over 2a, how many solutions are we going to end up with to that equation? So we take negative b and we add some positive number, and then we take negative b and subtract some positive number. So how many different numbers does that give me? Yeah, it gives me two numbers, right? I get one answer from adding, and I get one answer from subtracting, right? And there's nothing else in that equation that's going to give me more or less answers. And so if the square root, or if what's under the square root is positive, I get exactly two solutions to this formula, or this equation. So that tells me that f of x has two x-intercepts. So the graph is going to look something like this, or like this, right? In particular, it's going to intersect that x-axis exactly 2 times. And this is sort of what we're used to. Most of the ones we've looked at are like this. We end up with 2 solutions. But there are other possibilities. If your discriminant is 0, so if b squared minus 4ac equals 0, we're in a situation where we're like x equals negative b plus or minus the square root of 0 over 2a. So remember, when it was positive, we got one solution from adding, one solution from subtracting. What's going to happen here when I do like negative b plus 0 and negative b minus 0? What do you get when you add 0 to negative b? And what do you get when you subtract 0 from negative b? So you only get one number, right? Because adding and subtracting 0 gives you the same thing. So like it almost eliminates the part that uses the plus or minus. And so we only get one solution for x. Just because adding and subtracting 0 gives us the same number. So f of x has one x-intercept. So this is going to look like this, or like this. So where it just touches the x-axis one time. So it doesn't go through it, but remember, an x, like when we think intercept, we think of passing through something, but remember the x-intercept is really just any point that has a y value of 0. And so when we like bounce off the x-axis, we have one y value, or we have one point with a y value of 0. In particular, remember when we did 7.2, that activity, that x squared, like just the basic function x squared, is going to have a discriminant of 0 because it only touches the x-axis at 0, 0, right? So at the vertex. And then there's one other possibility, which is if my Bluetooth would work here. Let's see. If, there it goes, the discriminant is negative, so if I have b squared minus 4ac is less than 0, well, let's just kind of look at it. if I have x equals negative b plus or minus the square root of a negative number over 2a. So if you think back to when we were finding domains and there were square roots involved, what can we say about numbers you can take the square root of? Yeah, you can't take the square root of a negative, right? And so if we calculate what's inside the radical and then we try to evaluate this expression, we're not going to get a number. We're not going to get a real solution. We'll just get an error. So that means that our equation ax squared plus bx plus c equals 0 is going to have no real solutions. It's true there are complex solutions. We're not dealing with complex numbers here because they're not applicable to the graph of the function, right? When you look at a graph, it's just two real number lines, like perpendicular to each other, the x and y axis. Complex numbers are not on graphs. So that means that even if you get complex solutions, it still doesn't give you any x-intercepts because you can't plot complex numbers. So we end up with no x-intercepts. So f of x has 0 x-intercepts. So that's like where the entire graph is going to be above the x-axis, or the entire graph will be below the x-axis. It never actually hits it. So, and we figured all of this out only by looking at that piece under the radical. So what that means is, like, I don't need this whole thing to determine how many x-intercepts it's going to have. I do need it to figure out what the x-intercepts are, but in terms of classifying the graph as one that passes through the x-axis twice, just touches the x-axis and bounces back down, or doesn't ever touch it, all I need is the discriminant to determine that. And so we can figure out sort of how it behaves in general with respect to the x-axis just by looking at b squared minus 4ac, which is kind of cool because it's less work. Yes?
The discriminant was under the square root.
Yes, not including the actual square root itself. It's just b squared minus 4ac. So an example of something you'll see, like as far as a problem, is like use the discriminant to, what did I say? Determine the number of x-intercepts and I could replace the word x-intercepts with real zeros, so the number of real zeros as well. Remember, because the x-intercepts just have the x-coordinates that are the zeros. Yes?
So if we have this in the test, can we just write the b squared minus 4ac?
Yes, that is exactly what I want you to do. In fact, if you do a whole bunch more work, then you're not using the discriminant. So yes, that's exactly it. For the graph of f of x equals 10x squared plus 9x plus 23. So, like, I mean, that's a nasty function, right? With, like, the numbers aren't super pretty. I don't really want to factor it. I don't even really want to, like, do a whole bunch of, like, calculations with respect to, like, finding the actual solutions. So I'm just going to say, okay, b squared minus 4ac. That's my discriminant. That is equal to 9 squared minus 4 times 10 times 23. I'm not going to do that in my head. I'm going to let you guys punch it into your calculator. What do we get? It's an ugly number. It's not.
Negative
Yeah.
839.
Yeah, it's some big, huge 839, like some big, huge negative number. But in particular, it's negative, right? And what does that tell us about my x-intercepts? Yeah, there aren't any, right? If the discriminant is negative, then the function does not have any zeros or real zeros, which means that its graph does not have any x-intercepts. So that negative tells me that there are no x-intercepts. So like you'll see on your homework tonight, like what the test questions will look like. It just says something like this, and then it asks for the discriminant. You'll tell me what the discriminant is, and then you just use that to conclude how many x-intercepts there are. So it's a bit of a plugging and chugging thing, but also kind of interpreting what that discriminant actually means. So there's one other thing you can do with the discriminant, which is not something we're going to explicitly test you on, but it's a nice thing to have when you're factoring polynomials. It's actually how I use the discriminant most often, like more often than even doing this. It actually tells you if polynomials can be factored or not. So if the discriminant, is a perfect square, then ax squared plus bx plus c can be factored. So perfect square is like 0, 1, 4, 9, 16, 25, 36, right? Those integers squared. And then if it's not, then ax squared plus bx plus c is prime. So this is actually super handy because if you have a problem like factor 10x squared plus 32x minus 51, for instance. Well, if we were going to try to factor that, we would say AC is like negative 510, and then you have to make a list of all the pairs of numbers that multiply to negative 510, add them together, see if any of them add to 32, and if they don't, it's not factorable, and if they do, then you can factor, right? So that's a bit of a tedious process when you have numbers that are this big, right? So it's really handy to know if you can factor before you actually go through the process of making that whole list and like figuring out what your two numbers are. So if I find the discriminant, so b squared minus 4ac is equal to 32 squared minus 4 times 10 times negative 51, and you plug that into your calculator, what do you get? It's nasty. 3,060. So 3,064. And so then you're like, how the hell am I supposed to know if that's a perfect square? Well, you just use your calculator. So if you put in the square root of 3,064 and you get a decimal, then it's not a perfect square. And if you don't get a decimal, then it is a perfect square. So what do you get?
Decimal.
You get a decimal. So this is not a perfect square. Which I figured out because putting this into my calculator gets me a decimal. So what that tells me is that 10x squared plus 32x minus 51 is prime. It took a little while because we wrote this all out, but if you were just doing this problem, like if I just asked you to factor that polynomial, you could just real quick punch into your calculator 32 squared minus 4 times 10 times negative 51, try to take the square root, be like, oh, that's a decimal, it's prime, I'm done, right? So it just saves us a lot of kind of tedious calculations of figuring out if it's factorable before we actually try to do that. If we know it's prime, we don't have to do much work. So on the flip side, if I said to factor like 13x squared plus 131x plus 10. So again, these numbers are huge. I would really like to know if this is going to work before I actually try to do it. And so I do b squared minus 4ac equals 131 squared minus 4 times 13 times 10. And what do you get? Don't be afraid of big numbers. They're ugly, but we can work with them. Something pretty huge, I think. What'd you get? 16,641. So everybody else got it? So it's not pretty, but what do you get when you take the square root of it? You get 129, right? So is that a perfect square? Yep. Because this is not a decimal. So that tells me that this can be factored. Now, actually doing it maybe still is a bit of a bear, but we're going to talk on Monday about some ways that we can actually use this information and the quadratic formula to actually factor these polynomials that have really big, ugly numbers in them so that we don't have to use the AC method and make that big list. So for now, we just care whether or not it can or cannot be factored, and then on Monday we'll talk about how to deal with these ones that have really big numbers so that we don't have to go through quite as much work to actually factor it. Like I said, this part of it is not going to be explicitly tested on it. Like, I'm not going to be like, can it be factored? It's just a really good tool to have in your back pocket. So when you need to factor something, you can figure out if you can actually do it or not before you go through all the process of trying to do it. So tonight on your homework, it's essentially the same as